In this nutshell, I give an overview of the universal synchronous-asynchronous receiver transmitter. I explain what the USART is and how it can interface to other devices. I look at the data packet and how the data is sent. I explain parity error checking. I look at the clock format in asynchronous and synchronous modes. I look at the baud rate, the transmission modes, and I show a circuit. Remember, if you find this video useful, please like and subscribe. The USART is a serial communication system that's found in most microcontrollers. It allows us to transmit data over a single data line. The USART consists of three systems: a transmitter, a receiver, and a clock generator. A shift register is used to shift the 8-bit data out 1 bit at a time. This is then sent into a receiver shift register, and when the data has been received, it's converted back into an 8-bit data. The clock generator provides the baud clock. Note that in asynchronous mode, both the transmitter and the receiver must be set to the same baud rate. We can convert the USART to other serial data formats by using adapter modules, such as if we want to interface to USB, we can use the FTDI module. If we want to interface to Bluetooth, we can use the HC05 or the Microchip module, or to Wi-Fi, use the ESP8266 or the Microchip module shown here. The USART sends its data in a packet, which is shown here. Is in a specific format. We have an idle to start with that is always logic 1. We start with a start bit, which is always logic 0. Then we have the data bits, starting with the least significant bit, and we can have up to between 5 to 9 bits. Then we have an optional parity bit, and then we can have either 1 or 2 stop bits. Then we will either go back to a start bit if we're sending more data, or go to idle if we have finished sending the data. So we can see here the idle is always high, the start bit is always low, stop bit is always high. I have shown an example of sending 2 bytes down the USART. We are sending hex 5C, which is this binary number, and then hex F1, this binary number. It's important to realize that every bit in this sequence is a fixed known length, and we describe that by the baud rate. So then when we send a start bit, we know it's this length. Then this part here is the first bit, bit 0 of our data. This bit here is bit 1 of our data. So we know this because we know the fixed length of the bit. So we come along here and we have idle, which is always high. The start bit is always low. Then we can see bit 0, bit 1, bit 2, bit 3, bit 4, bit 5, bit 6, bit 7. Then the stop bit is always high. The start bit is always low. Then we send bit 0, 1, 2, 3, 4, 5, 6, 7. Stop bit is always high. And then we go to idle, which is always high. So we can see that there's a relationship between the bit length, which is the baud rate, and that is how the receiver determines each bit in the sequence. The USART can add a parity bit to the end of the data stream, and it is used to detect single bit transmission errors. The transmitter will automatically calculate and add the parity bit to the end of the data stream. The receiver will then check both the received data and parity and use that information to verify the data was transmitted correctly. There are two types of parity: even parity and odd parity. In odd parity, the transmitter adds a parity bit with either a 1 or a 0 to make the total number of ones in the transmitted data, including the parity bit, to be an odd number. So we can see here we're doing odd parity. We actually have an even number of ones in the data, so therefore the transmitter will add a 1 in the parity bit. Or if the data had an odd number of ones, then we don't need to change it, so therefore the parity bit will be 0. With even parity, the transmitter will add a parity bit once again to make the total number of ones in the data and parity bit to be an even number. So for instance, we're doing even parities. The data has an even number of ones, so therefore the parity bit will be 0. If we had an odd number of ones, then the parity bit will be 1. We can see an example of the error detection using parity. We're using even parity, and then we transmit the data 1100, 11000, so we have an even number of ones. Now we have a bit error here. We had sent a 1, but we had received a 0. Therefore we have a single bit error. The receiver will go through and say, there's an odd number of ones. We're doing even parity, so therefore we have an error. However, it can't detect 2 or more bit errors. So for example, we're sending the same data stream here. However, we have 2 bits incorrect, this bit here and this bit here. So now we have an even number of ones, so the receiver will think that that information was correct even though it has errors. The speed at which the data is transmitted is called the baud rate, and that's measured in bits per second. For example, a baud rate of 9600 means that 9600 bits are transmitted each second. There are a range of standard baud rates shown here. The USART can transmit either in synchronous mode or asynchronous mode. The synchronous mode, we have 3 lines: the transmit, receive, and the clock. The master sends the clock to the slave, and the slave will lock its own clock to the transmitter clock. Alternatively, we can do asynchronous transmission, where we only have 2 lines, transmit and receive. Each device then generates its own baud rate using a crystal controlled clock. For reliable communication, both the transmitter and receiver must be set to the same baud rate, and their baud clock frequencies must closely match, typically within a few percent. There are 3 types of transmission modes: full duplex. Data can be transmitted and received simultaneously, allowing communication in both directions at the same time. For instance, a phone call. We have half duplex. The data can be transmitted in both directions, but not at the same time, such as a 2-way radio. And finally, simplex, where the data flows in only one direction, such as a TV broadcast. We can see a schematic of the USART system interfacing to a UART to USB converter, the FTDI FT2325L chip, and that goes out to a USB socket. So we can see the receiver is connected to the transmitter of the device that is connected into, and the transmitter from the micro is connected to the receiver
of the device that we're connected to.